Hello friends, in previous lecture we have studied about the language of chemistry and the atomic structures. In today's lectures I am going to describe the basic concept of volumetric analysis, normality, molarity, molality, percentage strength, mole fraction, titrations and etc. We will also solve the basic multiple choice questions those were asked in your previous entrance examination. I have also selected some of the important multiple choice questions from the Indian entrance examination book. Let's start now. Before dealing with the titration process, we have to know the basic concept of standard substance. Primary standard substance and secondary standard substance. These are two types of standard substance, and the solution of primary standard substance is known as primary standard solutions. Substances whose standard solution could be prepared directly by weight are known as primary standard substance, and their solutions are known as primary standard solutions. By weighing the required amount, we could easily prepare the solution of primary standard substance. For example, oxalic acid, sodium carbonate, potassium dichromate, silver nitrate, Mohr salt, these are known as primary standard substance, and their solutions are known as primary standard solutions. And here are different criteria for the substance to be primary standard substance: non-toxic, non-hygroscopic, non-deliquescent, and it should be available in pure form. It should be invariant in composition, either in solid or solution state. In both solid and solution state, the substance should have invariant in compositions. The composition of substance should not be changed in solid and solution state. And the substance should have high equivalent and molecular weight. These are the criteria for the substance to be a primary standard substance. And secondary standard substance. Secondary standard substance are such type of the substance whose standard solutions could not be prepared by directly weighing, but they are prepared by titrating with primary standard solution. With the help of primary standard solutions, the concentration of secondary standard solution is quantified. To calculate the concentration or strength of secondary standard solution, we have to depend upon the primary standard solutions. Only then we could easily calculate the secondary standard substance or secondary standard solution concentration. Sodium hydroxide, HCl, sulfuric acid, nitric acid, and potassium permanganate are the example of secondary standard substance, and their solutions are known as secondary standard solutions. Remember, the strength of such type of the solutions could be calculated by using primary standard solutions. Titration. What is titration? Titration is the process to determine the strength of unknown solution with the help of standard solutions. With the help of primary standard solution, we could determine the strength of unknown solution. Strength means concentration. So this process is known as titration. For the titration process, we have to use two types of instrument. One is known as burette. This one is known as burette, and this is known as conical flask. And the substance or the solution which is placed inside the burette is known as titrant. Titrant. And the solution which is kept in the conical flask is known as titrant. Titrand, or it is also known as titrate. Titrate. So this is the general instrumentation of titration process. This one is burette and this one is conical flask, and the solution kept inside the burette is known as titrant, and the solution kept inside the conical flask is known as titrant. And the unknown solution means such type of the solution whose strength is not known, and it is generally placed in conical flask. And the solution whose concentration is known, that is known as standard solution, is kept in burette. So it is not the obligate case. We could also change the preparations of such type of the solutions either in the burette or conical flask. So it is not an obligate. We could also place the unknown solution in burette or in conical flask. Indicator. Thought substance added to the conical flask to determine the completion of reaction by changing color. We have to know the completion of reaction. To know the completion of reaction, we have to place or we have to kept a thought substance except titrant and titrant inside the conical flask, that is known as indicators. An indicator changes the color when the reaction is completed. So after the completion of reaction, the color of the indicator gets changed so that we know the completion of a reaction. Equivalence point. The point at which the equivalent quantity of titrant is added to the titrant is known as equivalence point. It is simple, right? The equivalent quantity of titrant is added to titrant is known as equivalence point. Here is titrant and here is titrant, and it is known as theoretical endpoint. The endpoint is the completion of reaction which is detected by changing the color of indicator, right? The completion of reaction which is detected by changing the color of indicator, right? During the endpoint or at the time of endpoint, the color of the indicator gets changed. So we will also study about the type of indicators. So the indicator is such type of the substance which color change after the completion of reaction. So after the completion of reaction, endpoint is obtained and the completion of reaction is detected by changing the color of the indicator. And titration error is the difference between the endpoint and the equivalence point. Endpoint and equivalence point will not be same. Equivalence point and endpoint may not be same, and there is some difference between the equivalence point and the endpoint, and this difference is known as titration error. It is mainly due to the indicator process. Indicator use or requires sometimes some of the time is required by the indicator to change the color after the exact amount of titrant is added to the titrant. So endpoint is obtained only after the equivalence point because indicator takes some times to change the color. However, the equivalence point is already obtained. Types of titration. There are 4 different types of titration: acid-base titration, redox titration, precipitation titration, and the complexometric titration. We will study one by one. First one is acid-base titration. It is also known as neutralization titration. In acid-base titration, the concentration of either acid or base solution is found by calculating the equivalence point of reaction with the help of sharp change in color of an indicator, right? And in acid-base titrations, either phenolphthalein or methylorange are most commonly used indicators. So in this type of the titration, we have to calculate the strength of either acid or base. Acidimetry. In acidimetry, the strength of acid solution is determined by titrating it with standard base solution. In acidimetry, the standard substance or standard solution is base, and we have to calculate the strength of unknown acid solutions. That is, the strength of acid solution is unknown and we have to determine it by using the standard base solution. In alkalimetry, we have to determine the strength of alkali solution, means basic solution, by titrating it with standard acid solution. In alkalimetry, acid is standard and base is unknown. We have to calculate the strength of basic solution. Here is concentration factors. It is also known as normality factors. So it is the ratio of the weight taken divided by weight to be taken. So weight taken divided by weight to be taken. Weight to be taken is also known as theoretical weight. So weight taken divided by weight to be taken is known as concentration factor or normality factor. It is simply ratio. Selection of indicator. this topic is very important. Indicators should change the distinct color near the equivalence point of the titrations. So only we know the completion of reaction after the change in color of indicators. If indicator does not change in the color near the equivalence point, then we do not know the end point of the titration, or we do not know whether the reaction is completed or not. So in this case, we have to select source type of the indicator which change the sharp change in color at the time of equivalent point of the titrations. Phenolphthalein pH range 8.2 to 10 and the methyl orange 3.1 to 4.4. So we have to focus only upon phenolphthalein and the methyl orange. So indicators are either weak organic acid or weak organic base. So phenolphthalein is weak organic acid and methyl orange is the weak organic base. So pH range of phenolphthalein is 8.2 to 10 and methyl orange 3.1 to 4.4. So it has pH range in basic medium, so it has pH range in acidic medium. The color of phenolphthalein in acidic medium is colorless, means it has no any color. However, in basic medium it has pink color. Similarly, the color of methyl orange in acidic medium is red and in basic medium it is orange. So while the process of titrations, if strong base and strong acid are used, then we could select either phenolphthalein or methyl orange as indicator. In case of strong base and weak acid, phenolphthalein is used as the indicator. Weak base and the strong acid, methyl orange should be selected as the indicator. And in case of weak base and weak acid, no sharp change in color at the equivalence point, so no any indicators are available. In some cases, phenol red is used as the indicators. So 4 to 10 pH and 6.5 to 10 here. So this 4 to 10 means at the pH range of 4 to 10, a sharp steep line is obtained in the titration curve. I will explain about the titration curve. This curve is known as titration curve, right? And this curve is related to the selection of indicator. And in y-axis, pH of the solution kept inside the conical flask, and in x-axis, the base which is kept in the burette. So pH versus strength of base is known as titration curve, right? So in case of strong acid and strong base, here HCl is a strong acid, right? In case of strong acid and strong base, initially the pH of the solution kept in the conical flask is very low, right? Nearly 1. Right? HCl is kept inside the conical flask, and from the burette, drops and drops of the bases are added continuously. And in initial process of the titrations, the pH of the HCl solutions kept inside the conical flask is very low. After the more and more drops of sodium hydroxide or the strong bases, in any type of the strong bases, sodium hydroxide is one of the important strong base. And from the burette, drops and drops of the bases are added in the conical flask. Then due to the presence of OH minus in the conical flask, the pH of the HCl solution now gets increased in linear fashion like that. And after the equivalence point or near the equivalence point, there is a steep rise in the pH of the solution kept inside the conical flask. So this steep rise in pH is known as equivalence point. So it marks the equivalence point. So after the equivalence point, there are no free H plus ion present in the conical flask. Then only OH minus is present, because more and more drops of the OH minus is added from the burette. Then due to presence of OH minus, there will be increase in the pH, right? So this is known as strong base and this is known as strong acid. So this one is the curve for the strong acid and strong base. So this line shows the equivalence point, steep rise in pH. So in these regions, there will be sharp change in color. So the detections of sharp change in color by the indicator is governed by this steep rise in pH. Due to the absence of H plus ion and presence of only OH minus ions, after the equivalence point, the line becomes straight toward the x-axis. So that the steep rise in pH marks the equivalence point, and HCl has equivalence point near 7, right? So HCl is a strong acid, and the equivalence point of the titrations between strong acid and strong base lies near 7. It is equal to 7. The pH will be in 7, and the range of the pH will be 4 to 10, right? This 4 and this is about 10. So we have to select source type of the indicator which has pH range between 4 and 10. It means either methyl orange or phenolphthalein could be easily used, right? The methyl range has pH 3.1 to 4.4, and the phenolphthalein has the pH range 8.2 to 10. Then these both lie between 4 and 10. So phenolphthalein and methyl orange, either of these type of the indicator could be used in strong acid and strong base titration. In the case of weak acid and strong base titrations, this one is weak acid. It is the representation of acetic acid, and acetic acid is an organic acid, and organic acids are general weak acid. And in initial process of the titrations, acetic acid has some higher value of pH than that of the hydrochloric acid because it is weak acid. It could not furnish as much as H plus ion which are furnished by the HCl because it is weak acid, so that the pH of the acetic acid is higher than that of the HCl. Then by the additions of the OH minus ion from the burette or the base from the burette, the pH slightly increased, and in these regions steep rise in pH occurs, right? So after the completion of the equivalence point, here is only base present in the conical flask, so the pH of that solutions will become constant. So it is the pH range of strong base which is added from the burette in case of weak acid and strong base titration, right? So this is the range, right? So this is above the 7, then we have to select source type of the indicator which has pH range 7 to 10, right? So in case of 7 to 10, what is the pH range of phenolphthalein? 8.2 to 10. So phenolphthalein could be easily used in case of titration between weak acid and the strong base because the equivalence point lies in the regions between 7 and 10 in case of weak acid and strong base. So in the process of titration of weak acid and strong base, we could easily use phenolphthalein as an indicator. And in case of strong acid and weak base, so let us know about this. So this is the pH range, or this is the pH range of strong base, right? This is the pH range of strong base. In case of strong acid and weak base, strong acid means HCl, and we have to know the weak base. For example, ammonium hydroxide, right? Ammonium hydroxide is a weak base. So in case of the titration between strong acid and weak base, initially the pH of the solution kept inside the conical flask is like the HCl solutions, right? Is this, right? Then after the equivalence point, right? The equivalence point, the pH of the solution present inside the conical flask starts to increase. However, it does not increase as much like that of the strong base because we have kept inside the burette a weak base. So weak base furnishes lesser amount of OH minus ion as compared to that of strong base. Then the pH range will be in this region, right? This region, right? This region. So this will be the pH range of the weak base inside the conical flask after the equivalence point, and this lies between this point and this point, right? So what is the pH range in this? So 4 to 7 point something, or 4 to 8, right? So in 4 to 8 pH there is what type of indicator available? So in case of 4 to 8, so phenolphthalein is not used in case of the pH range between 4 to 8 because phenolphthalein is used only after the pH 8 to 10. the pH range of the phenolphthalein is between 8 and 10. So phenolphthalein could not be used in this case because the equivalence point or the sharp steep rise occurs in the pH range between 4 and 8. So we have to use methyl orange because methyl orange has the pH range 3.1 to 4.4 and it falls between these regions. So methyl orange is used in the titration between strong acid and weak base. Similarly, in case of weak acid and weak base, this is the graph, right? This one is graph. So in these regions there is no any steep rise in the pH. There is some steep rise in pH, but in this region there is no indicator available. So we could not use any type of the indicator in case of the titration between weak acid and weak base. In sometimes phenol rate might be used, but it is not usual case. So in case of weak acid and weak base titration, no any indicator are used due to the absence of sharp change in color near the equivalence point. So these all processes are the selection of indicators in titration curve. Redox titrations. This is another type of the titrations. It is based upon the oxidation and reduction concept. The equivalence point is determined by sharp change in oxidant and reductant, which finally change the potential of the system. This is determined by using Nernst equation, right? We have to know the Nernst equation to calculate the potential of the systems. So this is the ratio of the oxidant and reductant. And here are different examples of redox indicators. Internal indicators, methylene blue and safranin. Self indicator, potassium permanganate act as the self indicator. We have to know this, this is very important. So in case of the titrations between potassium permanganate and the oxalic acid or Mohr salts, we could not use any type of the indicators because potassium permanganate itself act as the self indicator because it is in pink color. And the external indicator is potassium ferricyanate. So here is the reaction between Mohr salts and the potassium permanganate. This is an important example of the redox titrations. Right? This is Mohr salts and here is potassium permanganate. During the titrations, potassium permanganate changes to MnSO4, that is, it is reduced, and the Mohr salts changes to Fe2SO4 whole 3, that is ferric sulfate. The Mohr salts change from Fe2 plus to Fe3 plus, and the KMnO4 change from Mn plus 7, that is the oxidation number of manganese in KMnO4 is plus 7 to Mn plus 2. So iodometric titration is another type of redox titration. It is also an example of redox titrations. And in case of iodometric titrations, the standard solution used is hypo solution, Na2H2O3.5H2. It is known as hypo solution. And iodine, which is liberated from the potassium iodide by means of chemical reaction, is titrated against the hypo solutions. So iodine is liberated either from the potassium iodide or any other type of the compound or element whose strength is going to be determined. So from such type of the element or compound, iodine is liberated. This I2 is liberated, and this liberated I2 is treated against the standard hypo solutions. And here is the reaction between the titrations of a standard hypo and the iodine. So it is known as iodometric titrations. And the indicator used is stars, and the color of the stars will be changed due to the presence of I2 solutions, right? The color of the stars will be blue if there is presence of I2. And to give ions should be in highest possible oxidation state, right? It is very important point, right? To give iodometric titrations by any ion, it should be in highest possible oxidation state. We will discuss this concept in tackling the numerical problems, right? While we solve the multiple choice questions, we will tackle about this concept. Another is iodometric titration. Remember, iodometric titrations. It is not iodometric, it is iodometric. Here is IA. In case of iodometric titrations, standardization of solution is governed by titrating it with the given standard ionic solutions. So iodine is taken in the form of standard iodine solution, not in the form of the potassium iodide it is taken in the form of standard iodine solution, right? Iodometric titration. Another type of titration is precipitation titration. It involves the precipitation reactions, right? Here is a precipitation reaction between silver nitrate and sodium chloride. Silver chloride is precipitated out and sodium nitrate is also obtained. So in case of precipitation titrations, Moore's method, Bollard method, and adsorption indicators, there are three types of the indicators used in the precipitation titration. Potassium chromate is used in Moore's method, and ferric nitrate is used in the case of the Bollard's method, and adsorption indicator fluorescent dye is used in case of the adsorption indicators, right? It is very simple. And in case of complexometric titration, metal ion in the solution are determined by using complexometric titration. It is used in the case of determination of hardness of water, right? Complexometric titration. And ligand, here is one ligand concept, right? Based on the coordination chemistry. So ligand, complexing agent means ligand, right? In this case, EDTA is written, ethylene diamine tetraacetic acid. EDTA is one type of the hexadentate ligand, and this hexadentate ligand or EDTA is titrated with the metal ion to get a metal ion and EDTA complex, right? Metal ion and EDTA complex. In this case, in complexometric titration, indicators are also used. And the indicator in complexometric titrations are also the complexing agent, right? Also the ligand. Indicators are also ligand. So these are the different types of titrations. Acid-base titration is very important. However, another redox titration, precipitation titration, and complexometric titrations are not so important for you in the point of examination. First, concentration. What is concentration? Concentration of a solution refers to the relative amount of the solute and the solvent present in a solution. So concentration is nothing. It is the general expression of the amount of solute or amount of solvent. In general, amount of solute refers to the concentration. And percentage method is one of the important type of methods for the expression of the concentrations. Percentage W by W, W by V, B by V, and B by W. Here are different formulas for the calculation of percentage compositions. So you have to remember this formula to solve any type of the numerical questions. Normality. Normality is the number of gram equivalent of solute present in a liter of solutions. It means how much number of gram equivalent of solute is present in a liter of solution, which denote the normality. 1 liter of solution contains how much number of gram equivalent of solute. That is known as normality. And normality includes the volume. Here is volume, right? Here is the general formula for the calculation of normality, volume of solution in liters. So due to the involvement of volume during the calculation of normality, the normality changes with temperatures. In general, normality decreases with increase in temperature, right? Normality decreases with increase in temperatures. And here are different formula for the calculation of normality. Number of gram equivalent. Number of gram equivalent is calculated by using this formula. Mass of substance in gram divided by equivalent weight. And we have already discussed about the calculation of equivalent weight. And normality is number of gram equivalent of solute divided by volume of solution in liter. Similarly, here are different methods for the calculation of normality. You have to remember this formula to solve the numerical problems in any case. Basics for the normality equation, right? What are the basics for the normality equations? This is known as normality equations. N1b1 is equal to N2b2. If volume is kept in liters, then N1b1 is equal to the number of gram equivalent of acid or either base, and N2b2 is known as number of gram equivalent of either acid or base, right? This B is the volume in liter, right? Volume should be present in liter to get the number of gram equivalent. So number of gram equivalent of one substance is equal to the number of gram equivalent of another substance in any type of the neutralization reactions. Number of gram equivalent of one substance is equal to number of gram equivalent of another substance when these both substances are reacting together. So in that conditions, N1B1 is equal to N2B2. So normality of the mixture, either acid mixture or either base mixture, is calculated by this formula: N1B1 plus N2B2 divided by B1 plus B2. N1 is the normality of one type of acid and N2 is the normality of another type of acid. In case of base, N1 is the normality of one type of base and N2 be the normality of another type of base. In case of normality of the acid and base mixture, right, acid base mixtures, then N1 be the normality of either acid or base and N2 be the normality of either acid or base. If N1 is the normality of acid, then N2 be the normality of base, and a negative sign should be written here. Here is positive signs, here is negative signs. This negative sign refers to the neutralization process, right? Neutralization. Due to neutralization, negative sign is written because acid and base gets neutralized. Acid and base are neutralized in acid-base mixtures. If W gram of an acid is completely neutralized by V ml of the base of normality, then here is the formula: weight in gram of acid by gram equivalent weight of acid is equal to normality of base into volume of ml divided by 1000. You have to remember this formula also. When Va ml of acid of normality Na is mixed with Bb ml of base of normality Nb, then if number of gram equivalent of acid is equal to the number of gram equivalent of base, then the solution will be neutral. And if number of gram equivalent of acid is greater than that of number of gram equivalent of base, then the solution will be acidic. And if number of gram equivalent of acid is less than that of number of gram equivalent of base, then solution is basic, right? This is very important, right? This is very important concept. These all points are very important. Normal solutions means if simply n is written, then it will be normal solution, n by 2 semi-normal solution. You have to remember this, right? Molarity, right? The number of moles of solute present in a liter of solutions. 1 liter of solution contains how much number of moles of solute, which denotes the molarity. And molarity also involves the volume, so it decreases with increase in temperatures. Most common way of representing the concentration of solution, that is molarity. And when solute is diluted by x times, then molarity also decreases by x times. We will discuss this type of the topic later on. Number of moles is calculated by using this formula. We have already discussed in the chapter mole concept about this formula. Here are different methods for the calculation of molarity. Number of moles of solute divided by volume of solution in liters. These are different types of the formula. You have to remember this formula to tackle the numerical problems in any case. The relationship between normality and molarity, right? Normality into equivalent weight is equal to molarity into molecular weight. Next one, formality. For ionic compound, gram formula weight is written in place of molecular weight since they have no discrete molecules. Ionic compounds have no any discrete molecules. Ionic compound have no molecular formula. So in case of ionic compound, formality is written in place of molarity. However, the normality and formality are different things, but formality and molarity are the same things. A number of formula weight in a gram dissolved per liter of solution is known as formality. Molality. Number of moles of solute present in 1 kg of solvent, right? 1 kg of solvent. Remember, this is in solvent. This is solvent, not solution. It does not change with temperature because it does not involve any volume, and it is most inconvenient method. Molar solutions are less concentrated than the molar solutions. Remember this, and unit will be mole per kg. Here are different methods for the calculation of molality. Molality is equal to number of moles of solute divided by weight of solvent in kg. Remember, weight of solvent, and it should be in kg. And here are another formula. You have to remember this to tackle the numerical problem. Next one, ppm or ppb. ppm means parts per million and ppb means parts per billion. Here are different formulas for the calculation of either ppm or ppb. Weight of solute by weight of solution into 10 to the power 6 ppm, and weight of solute by weight of solution into 10 to the power 9. We have to remember this formula. Mole fractions, ratio of number of moles of one component, either solute or solvent, to the total number of moles of the solution. So this gives the mole fractions. It is ratio, right? mole fraction of solute is equal to the number of moles of solute divided by number of moles of solute plus number of moles of solvent. Mole fraction of solvent, number of moles of solvent divided by number of moles of solute plus number of moles of solvent. So the sum of the mole fraction of solute and the solvent is always equal to 1. You have to remember these relationships and you have to remember this type of the formula. These are very important to tackle the multiple choice questions. Relationship between mole fraction of solute and the molality, right? This formula is true only for the aqueous solutions. Here 55.5 refers to water, pure water, and x1 is the mole fraction of solute and m is the molality. A demol unit, 1 demol unit represents 1 mole of solute present in 1 liter of the solution at 0 degrees Celsius. It is simply a definition. An indicator used in titrations, I have already discussed about this. In case of strong acid and strong base, either phenolphthalein or methyl orange is used. In case of strong acid and weak base, methyl orange is used. In case of weak acid and strong base, phenolphthalein is used. And in case of weak acid and weak base, no any indicators are available. In some cases, phenol red is also used. In this way, the theoretical part of this chapter have been finished now. And we will start the multiple choice questions. Let's start now.